Welcome to Earth Science, everybody. So today, our third of three rock types. Did I just hold up four fingers? It looked like it. Third of three rock types. We've done igneous, and this idea might pop back up today. Igneous being rock that melted from one of the other three, forming magma that then cools and solidifies to form igneous. Sedimentary, the one near the surface, sediments make sedimentary, right? That one won't come up so much today. But metamorphic is going to be where there's enough heat and pressure to actually physically alter the rock, mangle the minerals, change them into different minerals, and give us what we call metamorphic rock. But even with all that heat, we can't get so hot that we melt, because if we melt, we make magma. So we got to kind of straddle that thin line, that thin window of enough heat to change the minerals, but not so much that it melts. That's the story for metamorphic rocks. Rocks that change due to heat and or pressure. We'll look at the environments in which that happens. If you've ever seen Gremlins, they use this term in the movie. They say that when it goes from this to this, I could have put a caterpillar and a butterfly, I suppose. Same thing. It goes through a metamorphosis, which I spelled wrong. Thanks. Thanks, computer. It goes through a metamorphosis from that to that, a change. We're going to do the same thing with rock. You go from sandstone, you put it under heat and pressure, it turns to a metamorphic rock from sandstone. We'll learn what it's called soon. There's two basic environments in which this can happen, in a simple sense. Regional metamorphism is going to be where we're going over a large area, and it's usually because of like tectonic forces. Spelling stuff for me today. I know we haven't done this yet. It's going to be fourth marking period, but there's the idea out there, I think loosely from middle school, that there's continents are sitting on plates that are moving around, and occasionally they ram into each other, and it's significant, the amount of force. We'll talk about it in just a sec. That's why it's called regional. It's over large areas. Contact is over a small area, and it's from nearby magma or lava, which is melted rock, which will form igneous, but if it's warm enough to alter the rock that it touches, you get some contact, some physical contact metamorphism. So where these occur, let's blow this up a little bit. Let's look at this one. This has happened multiple times through Earth's history. This is today's example. This is going on as we speak. India is ramming right into Asia. All right, I'm going to draw a couple arrows here to say that's essentially plowing into that. Head-on collision, right? If you've seen cars in a movie ever do a head-on collision, they hit and the hoods get all kind of crumpled up. That's happening here. A head-on collision of two continents, and the crust is getting all smashed up. And this gives us what presently today is the largest mountain range in the world, the Himalayas. All right, uplifted because of this collision, making it our tallest mountain range because of this collision, right? We'll talk about these tectonic collisions marking period 4. Today, we're just throwing the idea out there that, hey, deep within this, it's a tremendous amount of heat and pressure. If you get down, way down in here, it's melted. As these mountains build up, they also like drop down. You get the thickest part of the crust here. It's got to be balanced. It's called isostatic balance. Think of lying on a mattress. If you do, the mattress gives way a little bit. You get the thickest parts of the crust here, and where these two are really cramming into each other hard, you're going to form metamorphic rock. Let's loosely, imperfectly, say it's right about in that region right there. This is where you're going to form regional metamorphism. That rock there, whatever it was, is getting compressed under so much pressure that the minerals that make up that rock are being altered by those forces. If it comes down here and it gets too hot and it melts, again, not metamorphic, then possibly igneous one day. We're only talking about these. So how has a human ever seen one of these? Well, this has happened in Earth's history too. This is not totally unlike what happened with the Americas ramming into Europe and Africa. Boom, they collided. And they made a big mountain range like that, Himalayan-sized mountain range. which has then separated this whole Pangea separating thing. I know I'm jumping forward into Marking Period 4 a little bit, but you'll see it. And then weathering erosion for like a long time, way pre-human, has gone and wiped out the whole top of that ancient mountain range. Meaning that now what you see, like if you can cover up this top half right here, I don't want you to draw this on there because it might end up, well, that looks terrible anyway. It might end up confusing the diagram, but if you put your hand over the top half right there, eventually what wears away, you'll be able to see exposed those regional metamorphic rocks. So it's kind of neat, and that's why metamorphic geologists love this stuff. They're seeing the really, like the roots of mountains. They're seeing very old processes that have formed things in our old Earth. Smaller scale, over on this side, nearby magma or lava. So I don't know if I can tilt text boxes. Let's see. I tilt text boxes in Cami. If you can't figure this out, don't worry about it. This thing right here is an igneous intrusion. All right. We mentioned this at igneous rocks. Sometimes, because of tectonic things, melts from within the earth, plows its way towards the surface. Igneous, that melted rock, intrusion. It intrudes into older rock. I'll say that over here. Older rock. Older rock. Okay, so small scale. That little person is there to say we're talking not an entire mountain range here, regional metamorphism, just a little bit of rock near an intrusion. If it melted its way through, some of that would have gotten melted and incorporated into the intrusion. That's igneous, though, because it went melt, then back to rock. The older rock way away doesn't do anything, but the rock that's kind of right in that middle is going to be altered by that heat. Like it wanted to melt, but it didn't quite get there. The minerals got mangled by that heat. You may think this is something I'm making up to draw these little things, but this is like you're going to see lots of these diagrams, particularly Marking Period 4, with these little squiggles on it to represent. What does that mean? Little squiggle equals contact metamorphism. Okay, the older rock changed due to that, just really just the heat from that intrusion. All right, what do you think? So those are the big two. We can do it graphically too. This is a little intimidating, but graphically, what we'll say is this is just an XY graph like everyone you've done. You've done lots of them this year. Only the y-axis goes down, which works because we're talking about depth in the Earth. As you go deeper in the Earth, you're also going higher and higher and higher in pressure. So just take every XY graph we did where this is going up instead. Now we're going down to represent depth within the Earth. In all of these conditions, and I know this is complicated to look at this mathematically, don't panic. It's going to be okay. This area over here is basically nothing. These conditions don't exist. Nothing happens like it just doesn't happen on Earth. You can't get that deep without also increasing the temperature. So you can't be 20 kilometers deep in the Earth and only be 100 degrees C. It just doesn't work. It doesn't happen. Also, thinking about what we talked about up here, what happens if we go too hot in temperature? If we get way, way, way up there, you cross this line right here. This line is the melting point. So if you cross that line, you get melts. And again, if you do that, you've left the world of metamorphic rocks behind, which is fine, but it's just not what we're talking about in these notes of this lab. That's going to form igneous rock, perhaps one day. What I want to do is throw a couple more quick dotted lines on here, if you would join me, please. I'm going to do a little tiny one right here and put an S for sedimentary. That's where sedimentary rock can form. With a little bit of pressure, you need to like cement those sand grains, right, into sandstone. Getting up into higher pressure, I'm going to do another dotted line like this. I'm sorry, higher temperature. This little region up here, this thin region will be, we're getting way up there with temperature, but not really making the pressure go up all that much. This is going to be where you form contact metamorphism. The rest of this, if you do college geology, there's another one that's like way over here called subduction metamorphism. Don't panic about that. It never comes up at this level. We're not going to worry about it. The rest of this region is where you form regional metamorphic rocks. Again, it's not a physical area, it's a set of conditions. At these depths, which means these pressures, and at these temperatures, you'll start to form different metamorphic rocks. Now, I'm going to throw the names of some of them on there. And you might start to panic and say, "How this looks scary? How am I going to memorize all this?" Here's all I'm going to do. See this arrow right here? Here's your reference tables, by the way. Should look familiar by now because the other one looks a lot like this. I'm going to follow this arrow down with increasing heat and pressure. And as I do, it goes through the progression of these 4 rocks right here. So these strange words I'm about to write, they're just these 4 words right here. So don't panic. It's going to be okay. I'm going to decrease the font just a little bit here. The lowest heat and pressure regional metamorphic rock that we have on that table is slates. And then back up the heat and pressure more, phyllites. Back up the heat and pressure more, schist, S-C-H-I-S-T. Finally, jack up the heat and pressure some more. Nice, G-N-E-I-S-S. Right, roughly those conditions. You absolutely will not have to like memorize any of these numbers. There's a couple questions that you'll have in the classwork. It popped up on the Regents once, so they could possibly throw this graph at you, but it's pretty rare. But what could come up in questions certainly is that idea. But hey, just follow the arrow. Lowest heat and pressure to highest heat and pressure, top to bottom, is slate, phylite, schist, and gneiss. You'll be fine. Okay. All right. Next, this heat and pressure will compress rocks. I mean, think about it. We mentioned that Asia and India are ramming together. That's an entire continent with huge civilizations and tons of people. That's a lot of like mass jamming at each other. What's that going to do? If you're one rock in the middle, if you were this pool ball in the middle of all that, it's going to get smushed. If I had tectonically strong arms, I would take this pool ball and I'd scrunch it. I'd make it smaller. I'd compress it. So what that does is their density increases and their hardness, like resistance to weathering, increases. When we did the landscapes lab, remember that guy? We talked about the Adirondacks being the oldest rock in New York State and the highest rock in New York State. What's up with that? If they're that old, why haven't they worn away? Because they're very hard. They're metamorphic. They've had all that pressure on them to make the rock that hard. And they don't really break down very easily. The way that the sandstone over there at the Salmon River breaks down very easily. Go pull a piece out, no problem. It's soft rock. Yeah. So to pay attention to to do your job, what you're going to do when you grab this lab is really looking for texture, the texture of the rock, which remember, to a geologist, does not mean what it feels like, right? What does texture mean? Think about it for a sec. I'll grab a sample. This is igneous, but it's the same idea because texture is texture in geology. I'm not talking about how it feels. This feels rough. This feels smooth. That's all about how this thing has been treated since it was ripped out of the earth, right? Texture, through your geologist eyes, is looking at the grains of the minerals that make up the rocks themselves. So, like, basically, what is the crystal shape and size? Look at whatever the bits are that make up that rock and describe those textures. All right, and you're going to see 2 groups of them, ideally. This is a hard lab. I'm gonna help you a lot with this lab. I'm really gonna hook you up with the answers pretty straightforward. But I would like you to try to figure out at least a couple of the foliateds and a couple of the non-foliateds. So what does that mean? And again, oh my God, Finn, you're throwing more vocab at me. Don't worry. There it is in the reference table. Foliated means this. Foliated means that there are mineral alignments. And if you can do that at test time, just use that table. You don't have to memorize very much in this test at all. Foliated means mineral alignments, or perhaps banding is a type of mineral alignments. And when it's banded or when there's banding, there's bold stripes, easy to spot. The easiest foliations really to spot. Nice big bold stripes in it. Non-foliated, no mineral alignments. And really, again, I'm hoping you can spot that one. And I'm hoping you can give me a couple of these and a couple of these, maybe with a mistake or two. It'll be okay. But If you can spot a couple, you're going to get to the purpose of the lab. If you can work this table, you're really getting to the purpose of the lab. The foliateds have those. Here's the compositions. Type of metamorphism, again, there's the regional with increasing heat and pressure, or you could have these, some or both. Comments will have a lot to do with what it looks like, but it's not easy terms. Like this foliation surface is shiny from microscopic microcrystals. Nobody's ready to read that sentence and pick up a rock and say, oh, that's what that is. That's hard. It's difficult. I'm going to help. And in fact, then you can use that backwards to help. Like once we say, okay, this is this, and you got your fill lights, and you're like, what do I write in the lab? Well, that can kind of, you can use that to cheat a little bit. Schist, what do I write in the lab? Use that to cheat a little bit. Yes, platy microcrystals. You're going to see that with your piece of schist. Sometimes here quickly they mention the parent rock. Metamorphism of sandstone will give you quartzite. Metamorphism of limestone will give you marble, and so on. Okay. Coal you'll see again, and come up front to the front of the room. You're going to see the progression of coals going from the lowest heat and pressure, peat, up to now what we have is the highest anthracite coal. Because if you remember in the sedimentary one, you had the softer coals that showed up in there too. We'll check them out. You'll do great. Where we're going, we won't write much here, is to figure out what is the difference between sedimentary and metamorphic and igneous. You're going to have a whole bunch of rocks in this room and you'll figure that out. The hardest one is, hey, sedimentary layers of sediment versus metamorphic foliations of banded or aligned minerals. Can we figure out how to spot that? It's hard, but you'll do it. Give these questions a shot. They're just going to be mostly straight up practice on either this reference table, find things on here, or perhaps this rock cycle a little bit there too. You can do it. Thanks for sticking with me. You are ready for the lab. So long for now.